Hello, welcome back. In this segment, I will show you an example of how to prove theorems involving functions. Let's take an example. We all know that if x is equal to y, then f of x is equal to f of y. It makes sense if f is a deterministic function, right? You call f with some input x. We expect the output of calling f with the x is same as output of f on y, given that x and y are equal. We are assuming f is a deterministic function. Okay. So how do we prove this? If x is equal to y, f of x is equal to f of y. First, let me show you some syntax details here. This is the regular Z3 import star. We define two variables x and y as integers. These are mathematical integers. And we define a function f, right, between the domain integer and the range as integer. You can imagine, mathematically speaking, you have two sets here. You have two sets. Usually we draw something like this. F maps elements from here to here, something like this. The theorem is this, that if you take 2 points x and y and they are equal, that means this is your x and this is also your y, then we expect f of x is equal to f of y. This is basically what the theorem is, and we can let Z3 prove this for us. How do we do that? We make a claim here. If x is equal to y, implies, in math we use only one equal, in computer programming usually we use two equals, implies f of x is equal to f of y, and we negate it. Okay, we will negate it inside the proof function. If the negation is not satisfied, that means the original theorem must be true. That is the framework we prove things in Z3. Let's go into the proof very quickly. Proof takes a theorem, it instantiates a solver, it negates the theorem. If the negation of the theorem is unsatisfied, that means this is always false. This means this must be true. Okay, that is the idea. Otherwise, you get a counterexample. First, x is equal to y implies f of x equal to f of y. We will prove it with help of Z3 first. Yeah, it's proved. We all know this is correct. Okay, let's take another example where we cannot prove, so we will get a counterexample. Here we are defining a function f. The theorem is that if your x is equal to y, we are saying f of x is same as f of y. This makes no sense, but we will see whether Z3 can disprove this claim that we are making. Yeah, you get a counterexample. The counterexample has to be interpreted as follows. We need two numbers x and y such that x is equal to y. Do we get it? Yeah, it's 0, 0. Our theorem was f of x is equal to f of y. That was the theorem we had, but this is not a valid theorem. I mean, it's not satisfying. If the function f is constructed as follows, you see it's synthesizing a function for us as a model, okay? What it says is that you are having, say, 0, 1, and you map it to 0 gets mapped to 1, 1 gets mapped to 2, and everything else, there may be many elements here, right? Everything else, 0 is not used in the range, but that's fine. When x is equal to 0 and y equal to 0, what is this one? This is nothing but f of 0, which is nothing but what is f of 0? F of 0 is nothing but 1, so we get f of 1. And where is f of 1 mapping to? F of 1 mapping to 1 is mapping to 2. That means this whole thing is 2 when x is 0. Okay. What about f of 0? We just computed f of 0, which is nothing but 1. 2 is not equal to 1. Therefore, it was able to suggest this as a counterexample to make this theorem incorrect. Okay, that's all. So to sum up very quickly, all you have to do is create your function. Function itself is not defined. We are asking Z3 to come up with a function which either proves or disproves this claim. Okay. When it is disproved, you get a concrete function. When it is proved, you don't get a concrete function because it's true for all possible functions. That is the idea. Okay, that's all. Thank you very much.